Okay, so welcome everybody to the DV Club. Today we've added an extra session. We normally have 4 per year. We've added an extra one today to cover the latest VHDL verification techniques. Today we have 62 attendees. Everybody's remote. DV Club is still remote at the moment, no physical access. That represents 52 companies across 21 different countries. Okay. And today I'm very pleased actually. We've got 2 speakers, Espen and Jim, who are the authors of the 2 leading VHDL verification methodologies, UVVM and OSVVM. So our first speaker will be Espen Tallaksen from EmLogic, and the second speaker will be Jim Lewis from SynthWorks Design. And of course, as always, a thank you goes out to our sponsors, Agnesis, Brecker, Cadence and Synopsys, and to Tessov, who help us run these. Okay. So that brings me to the end of my introduction. I will stop sharing. And once our speakers have started sharing, I will do a first introduction. Okay. Looks like we're ready to go. So as mentioned, our first speaker today is Espen Tallaksen from EmLogic, where he is the CEO, based in Norway. He is the author and architect of UVVM, the leading verification methodology and library for VHDL. He has given lots of presentations at various international conferences with great feedback. He has also given courses on FPGA Design and Verification, and the title of his talk today is Get the Right FPGA Quality Through Efficient Specification Coverage, also known as requirement coverage. So over to you, please, Espen. Absolutely.
Right. Thank you.
Go ahead, please.
Can you hear me?
Yes, we can. Go ahead, please.
Right. Great. So thank you, Mike. Just before I'll start on the presentation, I'll just briefly mention that I'm from a company called EmLogic. It's an independent design center for embedded systems and FPGA, as you said, based in Norway. We were established only 3 years ago. So we had quite an extreme ramp up now to 44 persons. We're a verification IP and methodology provider, UVVM. And as you mentioned, we also do courses on both FPGA design and VHDL verification. And in fact, the next course on VHDL verification will be in less than 2 weeks. You can check that out on our website. So, to UVVM, what is that? Well, it's a universal VHDL verification methodology. It's a VHDL verification library and methodology. It can be used for FPGA, ASIC, and CPLD. Free and open source. It's being used by approximately 40% of all VHDL designers worldwide. And it has a very structured infrastructure and architecture and allows the users also to make test benches with a good architecture. So it significantly improves verification efficiency and assures a better design quality. It's recommended by dualists for test bench architecture. We work a lot with ESA, the European Space Agency, to extend the functionality. And as a matter of fact, we started a new UVM extension project only a few weeks ago. It's available on GitHub and on IEEE. And it runs on any VHDL 2008 compliant simulator. And we have a tight cooperation with Siemens, Aldec, and GHDL to make this work on all platforms. So, just a brief introduction to the tool itself. I just want to show you an example of a test sequencer code and the transcript log for that, for a really simple case, just to see, to give an impression of what you can do at a sort of really simple level. So, if you look at the test bench for an interrupt controller, for instance, an interrupt controller with a clock and a reset, a simple bus interface, that's a processor interface, some interrupt sources coming in and a resulting interrupt going to the CPU. When making a test bench for that, of course, the first thing you need is a clock generator, and you can take that directly out of the UVVM utility library, just as a concurrent procedure, and put that in your architecture, and you have a clock generator. And then, of course, you have a test sequencer that you want to use to test everything inside your module. And one of the most important things you can do in any test verification methodology is logging and alert handling. So we always start with a log. In this case, checking, for instance, the interrupt trigger clear mechanism. And then in the transcript window, we'll get a transcript of that. And then we can do a simple check value to check that the interrupt to the CPU is 0. And then we have a mandatory comment string that also then goes into the transcript. This is because that makes the test bench running, debugging, and everything much simpler. So we have a time-stamped recording of what's happening inside your test bench. This can, of course, also be removed by verbosity control. You can check for stability, for instance, to check that the interrupt to the CPU has been stable since the reset time in this case. And that's something you need to do quite often. And if in this case, of course, you want to generate interrupts, so you generate pulses on the interrupt source, setting it to 1 for 1 clock period. And then you have the same transcript in the log window below. One of the most important things you have to do in a test bench is to wait for something to happen. So in this case, waiting for an interrupt to the CPU to go to 1, at the earliest after 0 nanoseconds, at the latest after 2 clock periods. And these timeouts are extremely important because otherwise test benches have a tendency to just stand there hanging and waiting for something that never happens. And just a simple example also of a bus functional model, in this case, the simple bus interface write access, writing to a given address, a given value, and with a, in this case, given comment. So this is just a simplified transcript. There are more in the actual transcript, like a prefix, message ID, and scope, and so on. And all these procedures have a positive acknowledge if you want that. Otherwise, you can remove them. An alert message and mismatch report. And of course, counting alerts and controlling them. There are lots of free bus functional models and verification components in UVVM. So it's the largest collection of VHDL interface models. They are also all free, all open source, well documented, and so on. And there are example test benches for all of these. By the way, the example test benches, a lot of them will be located in the repository called UVVM Supplementary. So what enables quality and efficiency? This is an overview that I'm showing and talking a lot about in our courses because it's extremely important. And I think there's a huge improvement potential for more structured FPGA verification. So overview and readability is extremely important. And of course, also modifiability, maintainability, extensibility. And debuggability might not seem that important, but people actually spend 25% of the total project on debug activities, according to Wilson Research. And of course, everyone wants reusability. And then to achieve this, you have to get a good structure and architecture. I talked about that, but you also have to focus on simplicity where it matters the most. And UVM targets all of this. So we have the utility library with the functionality you saw on the previous slide, the bus functional modules, from which you just saw one case. You have watchdogs and monitors, error injection. You have constrained random and functional coverage, of course. You have verification components. And for these verification components, you can use transaction level commands. And of course, you can also use scoreboards. And then you have, as I said, all these different BFMs and verification components. And of course, also specification coverage, which is a target topic for this presentation. So let's start on that. So what is specification coverage? It's something you use to assure that all requirements in a specification have been verified. It's also known as requirements coverage, or requirements tracking, traceability, and so on. It has several similarities with functional coverage, but it's not the same. So most requirements can't be marked as verified or covered just from one or a few values. So most often, specification coverage involves multiple test steps in a test sequence. You write to some registers, you set some inputs, you do something more, you check some outputs, and then after a while you think, yes, I have covered this requirement. And of course, application area and customers often require different reporting views. I'll come back to that. So we want to ensure that all requirements in a specification have been verified. That means, of course, that the first thing we have to do is to specify all requirements. This is a really simple example with only 4 requirements to motor control, where you have a requirement to acceleration, top speed, deceleration, and final position. There would, of course, be lots of other requirements as well, but this is just to show a simple example. Then you want to report coverage from the test sequencer or any other parts of your test harness. And then you want to generate a summary report for that, showing you which requirements have been covered. And for that, you can list coverage per requirement. You can list test cases covering each requirement and requirements covered by each test case. This is a so-called requirements traceability matrix. And this matrix is mandatory for safety and mission critical designs. And it's also something that ESA has as a strict requirement. I would say it's also strongly recommended for any FPGA where you want to have good quality. And there are expensive tools existing for this, but this with UVVM is free and open source. So there are actually also free solutions existing to report that, for instance, a test case has finished successfully. But reporting a test case has finished is not sufficient. Because that means if you do that, basically you're just verifying that this simple test case has finished and make a report for that, and you accumulate all of those reports. But what if multiple requirements are covered by the same test case? So in this case, for instance, we would be moving or turning something into a given position. We will first have acceleration, top speed, then deceleration, and a final position. So of course we could do that with 4 different test cases. And then we get a report for each of those, and we can accumulate those reports to give us some kind of specification coverage. But this is not efficient at all, because in fact, we could do all of these things in sequence. And that would, of course, give us a far more efficient verification. And then, of course, generate various types of reports, like this requirements traceability matrix. So an example case, just jump to a different case here with the UART, and again, showing just a few requirements for simplicity. I won't go through the different requirements, but we have 4 requirements. And I'll start by showing you a single test case testing all requirements, just to give an introduction to this tool. So this is an overview of the tool, quite simplified, but we start by extracting requirements. We have to get that, of course. And we make a file out of that, a requirement list with the requirement label and a description. Could also include the test case. And the gray rectangle to the right, just showing you the syntax of the file. So then we implement the test case. And you can see inside the test case sequencer here on the right. And the first thing we do is to initialize requirement coverage in this. And when we do that, we also make a test case partial coverage file. And the syntax of that is given to the right. So when we do our test sequences to verify something by, again, setting some inputs, writing to some registers, reading some registers, and checking some outputs, Then when we've done that, we can tick off that a given requirement is covered. So in this case, we do some testing and we tick off UART requirement 1 and 3. And we can see that in the test case partial coverage file. Continue with some other tests. And again, these could either, these could fail in the command, or it can fail due to, for instance, an unexpected alert. And if that happens, this partial test case coverage file will be stamped as failed. We continue doing all the tests we need to do to cover anything that this test case should cover. And then we end this test case by finalizing the requirement coverage. And that is the command that puts the stamp at the end of this test case coverage file. Then we can do that for multiple test cases. And then at the end, we run a specification coverage Python script, gathering all the different partial test case coverage files into a summary. And in this case, you can see one specification coverage summary in light blue here, which is the requirements versus single test case view. You can also have the different views I talked about previously, but as this is everything in a single test case, basically in this case, only the first report is of value, but it's just to show you the simple example. So with multiple test cases and simple usage, we can do different things. So normally any test can be run in any test case. Normally there's no requirements to that. And for every single test case, we need to initialize requirement coverage, tick off it, and finalize. It can all use the same requirements list, and then I have a unique coverage file per test case. So then we'll have, for instance, in this case, a one for the T basic coverage, 19K2 coverage, and T reset coverage. Not really good names and not really good separation, but it illustrates the usage. Then we'll run the Python script as before, but we include all the coverage files. And in this case, then we have the requirements versus single test case. We have requirements versus all covering test cases and test case versus requirements. So now we have all the different views, and it makes sense because now we have multiple test cases. So for advanced specification coverage, we may specify required test case for any given requirement. We may specify that at least one of multiple test cases must pass. We can specify that the requirement is tested in multiple test cases. We can even map requirements in one file to requirements in another file. And that allows us, for instance, reusable test benches with the coverage included. And it also allows compound requirements to split into multiple more detailed requirements. Some more features you can run without requirement file even. That could be initially or for just testing. Then, of course, you will not be given any coverage, but you will get a list of the tests. You can have multiple test case sections inside the same test sequencer, but then, of course, you need to finalize and initialize for every single section. We can have selectable strictness level. That's important because at strictness level 0, any passed requirement is compliant if run in any test case. For the next level, a passed requirement is compliant only if it's run in a specified test case. And for strictness 2, which is very seldom used, a passed requirement would be non-compliant if it's run in a non-specified test case. Let's show you a really brief step-by-step demo on how to get started with specification coverage. This is just the definitions you have to make up front with IEEE and the UVVM utility library. On top of that, you have to specify the VIP specification coverage library and include those packages. You'll have a few local adaptation packages where you can, for instance, set the max line length and the CSV delimiter, for instance. And of course, you would recommend to use constants for all the file names. The simplest case where we specify the requirements would be like this. We have the requirements in the requirement file, only 2 parameters where the test case here is not specified, which means it can be run anywhere. We'll have a single test case only in this case, and with all requirements covered. This is the command you would run, the initial requirement coverage with the test case requirement file and the partial coverage file. And for demo purposes, I will reduce the transcript and skip, for instance, the message ID column. Then it would look like this, where the first response on initialized requirement coverage would be reading and parsing the requirement file, then listing all the requirements and the descriptions, and then closing the requirement file. And then coverage for the simple case, you would start looking at the test sequencer itself, and then tick off the requirements as you have covered them. So you do some relevant checks, you tick off requirement UART requirement 1, then you'll get this logging the requirement UART requirement 1, and it's passed. And then you can do the same thing for requirement 2, 3, and 4, getting the same type of output, and continue on the requirement 5, same kind of output again. And then you close everything by doing the finalized requirement coverage. And you can see that everything is finished checking. This results in a partial coverage file. It has some information that's not so important, so I'll just remove that to make it simpler in this view. And then the partial coverage file will look like this. So the test case name, the different requirements, and whether they passed or not, and a summary. Then a summary for this simplest case. You run the Python script like this with the requirement list, partial coverage name, and the summary name. So in this case, you can see the summary and number of compliant requirements, actual compliant requirements, the passing test cases, and in this case, I was, of course, test case 0. And then again, the partial coverage file and a summary. We can even make it simpler than the simplest, where you don't need the requirement file and you don't want to use that. Then again, you can initialize requirement coverage, and when included in the requirements file, it will look like this. Without requirement file, it will look like this, and the only difference will be the descriptions. So there's really no change to the partial coverage file. Now with the test case specified, then you include that all these should be tested with test case 0, and then you get a partial coverage file, which is again exactly the same as previously, because it's always specifying which test case is running anyway. Now with multiple test cases, which is the next level, you have a requirement list. Again, 2 parameters only, test case not specified. So you have here you have test case 1, exactly as we described before, with the requirements and logging requirement UART requirement 1. Test case 2 logging the 4 other requirements, and test case 3 other requirements again. And now you can see for these 3 test cases that you have covered different requirements in the different files. So you want to prepare post-processing, so we could, for instance, list all the partial coverage files in a single text file like this. And rather than including all the arguments in the command line, we can make a config file like this, where we include the requirement list, the partial coverage files, summary, and so on. And we could also include the requirement mapping file and strictness. Then we can make coverage summary, again with this Python script. And you can see now we don't have all the parameters, we only include the config file. Now we have the configuration. You can see that the change from the previous example was that we have a partial coverage file and we have a config file. And the summary will show you again that the number of compliant requirements and the number of passing test cases. And then, of course, you'll get the summary, in the different files, and you can check, of course, the partial coverage files and the total summary file. So to conclude here, specification coverage does not in itself say anything about absolute quality. It depends on the developer really testing the right stuff. It depends on a good requirement specification where all relevant requirements must be included, and compound requirements should be split into testable sub-requirements, which is easy to do with this mapping feature in UVVM. And given good test cases that do what they are intended to do, then specification coverage will track and assure that all requirements in the specification have been verified. And that's the most important thing here. Because it is quite common to just sometime during development tick off somewhere that a particular requirement is tested. And very often this is just done as a mental exercise, which of course is not good at all. So it's always better to use a written, repeatable, and automated approach. And this specification coverage IP definitely simplifies such an approach and gives you all the features you need to satisfy any requirements from ESA or any requirements for DO254. Okay, thank you.
Thank you very much, Espen. So we just quickly look to see if there's any questions online. I have a couple of questions for you. So can I use UVVM specification coverage for various standards like DO254, for example?
Yeah, I mean, we have several users who have used that for DO254.
Okay. Any other standards? I know a lot of we do a lot of work for ISO 26262 automotive, for example. Can it be used for other standards as well?
I would think so. I mean, I heard of people using it for different standards, and I think it covers all the requirements to the standards I've heard of anyway.
Okay. And yeah, one final question. What happens, for example, if a test fails in one out of the two test cases and only one test case is required?
Say again, please.
So imagine you've got two tests mapped to a requirement, but only one test is actually required to pass. What happens if one passes and one fails?
Okay, if one fails, it will fail.
Okay, the whole thing fails.
So the thing about the requirement that you could set it up to only that you only need to test it in one out of three different test cases, right? And that means if it passes in one and you don't run the two others, that's acceptable. But if it fails in one of the two others, then it fails.
Okay. And
this is, yeah.
What type of mappings are available? For example, many-to-many is possible under this scheme?
At the moment, it's one-to-many.
It's one-to-many. Okay.
Yeah.
And is it unidirectional or is it bidirectional, the mapping?
That is also currently unidirectional. You can split a compound requirement into multiple sub-requirements, and you will get a test report or specification coverage report for the sub-requirements and for the top requirement.
Okay, that makes sense. Okay. Okay. We will leave it there. Oh, there's one more question. Sorry. Is it possible to summarize the coverage of test cases which are run separately via VUnit?
Yeah, no problem at all. You can run it with any system you like. It's all a matter of just specifying where the partial coverage files are in the test coverage text file.
Perfect. Okay. So thank you very much, Espen. And we'll finish there. And we'll move to our second speaker. Thank you.
Thank you.